Something that I'm really curious about now is conceptualizing this with just two continuous variables.
One answer is that it is directly analogous, right?
Okay.
But it's just a little bit harder to talk about because we can't say the big fluffy group, right? Because there's
Yeah.
bigness and there's fluffiness and they're just continua. And you can't plot it nicely like this, right?
Yeah.
Um, if you, because it wouldn't make sense to have a key that shows the different categories of your other, like two-dimensional plots are really nice if you have one numeric DV and two categorical variables, or one numeric DV and one numeric predictor and a categorical predictor that you could put in the key. But as soon as
Yeah.
you've got two numeric predictors, then there's no satisfying way to plot it unless you make a 3D plot.
Mm-hmm.
But you can think of it as being just like this. If you have your predictors and you're envisioning that 3D plot, then you've got, if you're holding a pencil in the three-dimensional space, a highlighter, right? Um, and let's, you can imagine yourself twisting the pencil as you move through the space.
Mm-hmm.
Like there's a positive slope between the X and Y over here, and as I move along the Z dimension, it continuously modifies that positive slope. So maybe it flattens out, or maybe it flips completely as I move along the Z dimension. Um, that is if you have an interaction between your continuous predictors.
That's pretty intense.
It is pretty intense to visualize it like that, yeah.
Yeah.
But luckily, you can still think of it as basically, if you include them both in the same model, then you are adjusting for the extent to which they're correlated with one another. So that at any given point along your covariate, you would predict that observed slope of a relationship between your main predictor of interest and your outcome variable.
Okay.
The same way we would have said in any given category along our fluffy, scruffy covariate in this example.
Okay.
Except now there's infinitely many points where we could make that prediction instead of just two.
Mm-hmm. Okay.
And if all you're doing is controlling for it as a covariate, statistically adjusting for it as a covariate, then it's like these dotted lines. You're
Mm-hmm.
restricting it so that the slope of your main predictor is the same at any point, and you're just allowing it to be different heights.
Okay. Okay.
On the other hand, if you have an interaction, then it's more like the solid lines here, except that you could imagine maybe degrees of fluffiness or scruffiness, and you could imagine this solid red line slowly morphing into the solid blue line instead of just two separate lines.
Okay.
When we say the interaction is statistically significant, in other words, the extent to which big dogs bark less than small dogs is significantly greater in the fluffy case than in the scruffy case. And I say significantly greater, I mean that if I were to calculate the discrepancy between those discrepancies, the difference between those differences, the probability that if I did a study like the one I did, under the conditions in which I did it, and there really was no interaction, the probability that I would obtain data as extreme as the ones that I obtained would be low, extremely low, which is what helps to convince me that that's not a compelling alternative explanation for the results that I got. That if someone wanted to say, well, maybe you only got this interaction because you purposely chose, you went to the dog park and people only bring their big fluffy dogs to the dog park if they don't bark a lot, because otherwise they're too scary. And you have a biased sample, that would be perfectly fine alternative explanation for my results. I can't really defend against that.
Mm.
Instead, someone came and said, I have an alternative explanation. It's just a coincidence. You just happened to get a bunch of big fluffy dogs who don't bark much by chance. And really, the big fluffy dogs on average they bark just as much as the small fluffy dogs. That I can argue against, because if that was true, the probability of getting the data that I got would be extremely low, less than 2 times 10 to the negative 16. Imagine someone arguing your results are just a coincidence and say, if that was true, the results I obtained would be extremely improbable. So you're trying to claim, you critics saying my results are a coincidence, are trying to claim that something extremely improbable happened. And I think that's worth my doubt.